Okay, good morning, everyone. I think we'll get started. So thanks so much for joining us today for our Digital Manufacturing in Orthotics webinar. I'm just going to run through what we're going to cover this morning and also introduce my fellow panelists. So we are going to cover off a quick welcome from me. My name is Sabina from CREAT3D. We're then going to cover off the use of additive manufacturing and a digital workflow in orthotics. We're then going to do some live scanning with Joe and Moises. Moises is then going to explain some of the additive manufacturing process, and we're going to finish with a Q&A. So at any point this morning, feel free, if you've got any questions, just to hit the Q&A button at the bottom of your screens, type your question in, and then we'll gather them all at the end and run through them. So a quick introduction. So myself, I'm Sabina Gonzalez-George. I'm Creative Marketing Director here. I'm joined today by my colleagues Seiko from Formlabs, Applications Engineer, Moises, Engineer from CREAT3D, and Joe from Measurements Solutions Limited, our scanning expert. So just to introduce our partners formally, so we have Joe from Measurement Solutions Limited. So they have 25 years of experience in metrology. So our scanning partner doing the scanning for us today, they have a huge wealth of knowledge as well in using metrology within manufacturing processes. Joe?
Yeah, thank you. My name is Joe Winston from MSL. Like Sabina said, founded 25 years ago. Started focusing on CMMs, sales and calibration of CMM hardware and software. In 2005, we started our strategic partnership with Preforming. We're the exclusive reseller for Preforming here in the UK. And in 2021, we took on the reseller role for NTOP as well. And NTOP mixed with Preforming gives us this really nice end-to-end workflow that we're going to show you today. So we're going to go through scanning, bring the scan data into NTOP to create some custom orthotics, and then hand that STL over to Moises and to the Formlabs team, who are going to run through and show you how to print it.
Thank you. And also we're joined by Formlabs. So we're one of the UK partners of Formlabs. Seiko here is our application engineer. Formlabs started back in 2011, developing and manufacturing SLA 3D printers, multiple generations moving forward of the SLA. They also introduced the SLS system, which we're focusing on today, and it's all behind me. So we've got the system right behind us, the fuse, the sift, and we'll be exploring that today. They have a huge focus on materials, and you'll see in front of us an array of huge number of items that we're going to explore today as well. So just a really quick introduction to ourselves. So we're CREAT3D. We are everything additive manufacturing. So we do a full end-to-end solution. We're passionate about additive. We're 10 years old this year, so we've got plenty of knowledge and experience and partnerships that we've been building over the years. We like to just get you started, get you cracking on it, and then work with you on your journey of additive. We're based in Berkshire, and this is our office, and we host loads of events, loads of workshops like these as well. Some of the things that we offer, really it's just everything you need, from advice and guidance at the beginning to get you in the right machine and the right equipment, and then it's all the way through, whether it might be applications engineering support, working with our partners, reverse engineering, looking at design for additive, answering your technical questions, supporting you, developing your strategy for the future as well. These are just some of our clients. It's our vanity slide. Everyone has one, I'm sure, but yeah, we work with everyone from small businesses all the way through to large corporations. We have clients that have been with us since 10 years, and we have a whole range, which really what that means is that we can share insights from different industries, but also just share insights from peers as well, so that we're just developing and growing. So back to the question and matter today. So why use additive manufacturing, and why use a digital process in orthotics? So really just to give a little bit of insight. So typically additive manufacturing, or AM as it might be called throughout today, is used across 3 areas. So from prototyping, production tooling, and then end use parts. Why? Tons of benefits really. Essentially it comes down to the fact that it's a complementary technology in your businesses. You can 3D print geometries that you can't traditionally manufacture. You see huge cost savings. Typically, we see figures about 94 to 98% in cost savings in tooling, for example. We also see big time savings. So by having 3D printing in-house, you are, reducing your lead times from typically 2 to 6 weeks to 1 to 2 days. And there's no minimum order quantities, which is also a huge bonus. And the other benefit that's becoming more and more important is that we're seeing digitalized manufacturing and localized manufacturing. So it's not kind of stretching supply chains, it's actually producing things on site, local to you, saving on waste and also storage. So particularly in orthotics, there's kind of 6 key reasons that we would bring it down to as to why look at a digital workflow in orthotics. So first one, massively important, is exact patient fit. So we know that this is incredibly important in the industry, but we can optimize parts to patients' needs. So that's with a combination, particularly of scanning at this stage. So you can scan your patient, then you can edit the file and edit the part to produce something that really fits perfectly. You can also look at then customizable and extendable designs for longevity. So you don't need to continuously replace a part. Actually, you can design it so that one section could be swapped out, could be extended, could be adjusted over time, particularly for young children and young adults who are going to continue to grow and change. Then we're looking at things like better product design. So this particularly is improved functionality and lightweighting. Lightweighting is particularly important here. So this is where things like the NTOP design software, generation design software will come in, because it will actually help to lightweight parts, combined with scanning and then printing, means that we can print these geometries that we wouldn't necessarily be able to achieve any other way. We've also then got really fast turnaround with really short lead times. So typically having this machine in-house, you're producing parts between 1 to 2 days, and you're not relying on external suppliers. You've also seen low cost and repeatable costs. So you could produce 1 or 1,000 units, and each unit could be slightly different, but your cost would be the same. So you know what you're paying each time. You're also then not subjected to third parties who might have to pass on raw material, big changes in raw material costs to you, or shortages in raw materials as well. And then finally, one of the big benefits with using additive is that there's no minimum quantity for manufacturing. So that means that you can produce 1 or 1,000 parts. You don't have to put in a minimum one. And especially within this industry, we're going to see lots of parts that are needed that are all going to be slightly different or have slightly different design elements within them. So really, that's a massive bonus. And one of the benefits about the technology we're looking at today in particular is that when you're building or you're completing a build, which Moises will explain later, that actually you can stack and you can nest parts. So you are maximizing your production space every time you do it. Just very briefly, just to introduce the Formlabs range, just to give a bit of context. So as I mentioned earlier, Formlabs cover 2 different types of technology, so SLA and SLS. So the SLA actually started back in 2011 with the Form 1 and has developed through the generations from the Form 1 Plus to the Form 2 to where we are today with the Form 3 Plus and the 3L, which is a larger version, and this is the SLA technology. There's also biocompatible designed machines as well, and resins, with a huge array of materials. They also then introduced the selective laser sintering, so the SLS technology, so the fuse and the fuse SIF behind me. And this is really focused on more complex geometries and low volume manufacturing, ideal for orthotics. And then finally, just to give some background on the materials. So I mentioned there is a huge array of materials, and Formlabs really continuously develop materials, which is a fantastic thing. And just gives us more scope and more usage as we develop. In particular as well, you can see there's a whole range here from general purpose through to the nylon powders, which we will explore later. But there's also the medical resins, which are really complementary to this industry. So you've got things like skin contact safe, biocompatible resins, and we have a lot of healthcare and medical device manufacturers as well who will also use this technology and these resins. So that's just a quick intro from me. Now I'm going to hand over to Seiko to dive into some examples of how the technology is used in orthotics.
Thank you. Thank you, Sabina, for the wonderful introduction. Once again, my name is Seiko. I'm an applications engineer at Formlabs, and I'm very excited to talk about some of the application in orthotics with our Fuse One Plus. So I'm not going to lie, I'm an expert in 3D printing, but not an all expert in orthotics. So I'm not going to try and teach you about orthotics. Instead, I'll give you a brief introduction of what we're seeing happening in the industry. So we see everything from the top of the head to the tip of the toe. And your current traditional or manufacturing methods may look something like this, where you start off with an input, whether it be with a foam box or a plaster cast, or even some sort of scanning. And then you have the data. You move on to the production with CNCing, thermoforming, usually subtractive manufacturing, sometimes additive manufacturing, but outsourced with larger machines. And then you get the final part. And today, what I'm going to introduce to you is the additive workflow with some of our partners here today. So what is it going to look like? You start with an image acquisition with a scanner like GoScan. After you get the scan part, you do have to design the part. There will be some designs we'll show you later on. And of course, a live session, which I'm really excited for. So you can use an array of softwares depending on your application. And a software today we'll cover is in topology. And of course, after you get the part, it's designed, you have the 3D file. What do you do next? It's 3D printing. I think Sabina's already covered a wonderful array of reasons why 3D printing. And I think this was some finding that I had recently when I visited one of my clients. It's that they had to maintain and keep plaster molds of patients for several years by law. And this is where a huge improvement can be brought about by just digitizing. So you don't necessarily have to have physical spaces of patient information. So let's not talk too much about the advantages because we've already covered that, but let's talk about some of the materials that we offer in a little bit more detail. I know it's a very text-heavy slide. I'm not expecting you to read all of it. I just want you to know that these are the materials that are currently available on the printers right behind me with the Fuse One Plus. Starting off with the furthest left, nylon 12. It's our most basic material. Most of our users use it. It's a material that does it all with high performance with good detail. There's also nylon 12 GF, which is greater stiffness, so it's good for thin walls. And then we have nylon 11, which I'll actually cover in more details in the upcoming slides. And then nylon 11 carbon fiber, which, as the name suggests, has carbon fiber in it. It's more utilized in the automotive industry, but it is great for strong, lightweight parts. And then TPU 90A powder. Again, don't worry, I went very quickly on this slide, but it's not meant for you to memorize all these slides. Let's talk about some of the ones that are quite interesting, specifically in orthotics, starting off with nylon 11. So nylon 11 is a high performance, high impact material. I have one here. I realize you can't see it because I'm very small, but I'll show it to you later on. But it's actually one of the most ductile materials that you need for bending, taking an impact. If I throw this across the room, it'll definitely not break and it'll come back to my hand if somebody picks it up. But I'm not going to throw that today, but you get the point. It is a material that is perfect for ideal for rigid insoles that goes inside the shoe. We actually did a lot more study for nylon 11, comparing ourselves to some of the materials on the market, like polypropylene, HP, which I will cover in the next slide. But what's another material that's heavily used in orthotics? And that's TPU 90A. TPU 90A, as you may guess from the name, it's an elastomer. It's resilient, it has good tear strength, and on top of that, it is 90A show hardness, which some of you may argue that's a very high show hardness, which means it's kind of too hard for your application. And this is where I really like our collaboration with Topology. So yes, the material itself has a show hardness of 98, but you can simulate other show hardnesses by introducing latticing. And that's where I personally use Topology. And this is a great example. The thicker part has a harder simulated show hardness, where a thinner part is much, much softer. And this is a very good example where you can actually simulate an array or a spectrum of show hardness thanks to design. This is especially difficult when you are doing CNCing. When you have a block of material, you're going to have one show hardness. If you want two show hardnesses, which I personally saw with one of the clients, they were using a foam that was two materials connected. It's brightly different colors, and you can try and replicate that simply by design. You don't have to switch out materials. So that's a great way how I use Topology personally. Just in case you guys are wondering, these two materials that I mentioned earlier, nylon 11 and TPU 90A, have been tested for cytotoxicity and they're not cytotoxic, they're not a sensitizer, they're non-irritant, and therefore we say it's a skin-safe product. But enough about materials. Now that we know the basic of materials, let me talk about some of the applications we see in the field. First off is rigid insoles, which I think I've already shown a little bit. What you see on the screen is nylon 11. It has been tested specifically against HP PA11, which is currently largely in the market for rigid insoles, and homopolymer PP, polypropylene. So we found that these materials, the nylon 11 that we offer, has withstand static 3-point bend testing, dynamic 3-point bend testing, Ross Flex tests to find that we are equal or even better in certain scenarios than some of these materials. So we found these materials to withstand 10,959 steps a day for 365 days, which far exceeds the steps taken by an average adult. So yes, we do have more test data. I'm not going to bore you with all the information. If you want to find out more about some of the test data that we have for rigid insoles, do check our website for rigid insoles orthotics at Formlabs, and you can find the full test report. So who's making rigid insoles? We have an example in Germany with CREAT3D. They are an orthopedic specialist medical provider. They have started to replace and produce 10,000 pairs with our 3D printer, the same one behind us. And essentially it solved and addressed the issues of shortage of skilled labor, the environment filled with dust and chemical fumes from all the subtractive manufacturing and the craftsmanship that was currently required. And it is a sustainability for 1,000-foot models. So that's rigid insoles. Let's move on to a similar example with ankle foot orthosis. It's used for controlling foot and ankle positions and accommodating fixed joints positions. I think you would know better than I do, so I'm not going to try and explain what it is. You guys know what it is. This is actually printed in nylon 12 simply because we needed a stiffer material. And this is a wonderful example that I personally really like, because it started off when one of the founders, Francisco, met a child that couldn't afford a ankle foot orthosis. And what they did was introduce 3D printing, which made it so much more affordable and so much easier to switch, especially if the child grows. And that's where 3D printing made a huge impact for this company and for these children. We have more examples like brace. You will actually see a live session of a brace being designed, which I'm really excited for, and I'm really jealous because it's going to be custom to this guy next to me. But braces are obviously going to be tailored and custom to the patient, and that's where, again, 3D printing plays a huge role. Who's doing it? Northwell Health, the largest health system in New York State. They use a variety of 3D printers and found our SLS to be the perfect fit for orthotics and prosthetic devices. But we'll talk more about braces in the upcoming demo. So let's move on to the final application in orthotics, which is cranial orthosis. So again, it's a special helmet to correct the shape of babies. Again, babies grow very quickly. You do have to adjust quite often, which makes it ideal for 3D printing. What you see here in the screen, and maybe in the camera as well, is actually TPU. So you can actually use a combination of different materials with a hard shell of nylon 12 surrounding with the TPU 90A lining. When I visited one of your clients at Created, they were going through the effort of having to shave down certain sections and tailor it to the patient, obviously. And that's where 3D printing plays a huge role, because you're not expected tedious time to carve anything into the shape of the patient. You essentially have a scan, you'll design it, you 3D print it. There's not much post-processing. And I think that's where a lot of the additive is playing a role in orthotics. Now we have other applications, and I know I ran through a lot of it very quickly, but don't worry, this is just an introduction. If you have any questions and you want to try out your application, you want to talk more in detail, feel free to reach out to the team at Created, and we can work together and find out the right material for you. I don't think this 10-minute presentation is going to find out the right material. Let's sit down and talk about it and find out what material your application will require. So that's pretty much it from my side, and I'm going to pass it on to the lovely Joe Winston for 3D scanning process and file preparation.
Thanks, Seiko. Right, so we've heard a bit of the at the theory of what we're going to see today. Now we're going to see a real life demonstration. So we're going to use our Preforming Go scan, scanner that we've selected to use today. The benefits of the Go scan is that it's a white light scanner, so it can track texture and geometry. It doesn't necessarily need targets to track. It can be really good at scanning body parts. We're going to take the scan data, bring it into NTOP, and create a custom orthotic for Moises here. So let's get started. Just going to share my screen here. Workflow. Okay. If I can get you to go up here, still for us. Start up the scanner. The go button. And we're just going to work around the arm. Yep. Data sets we need. The Go scan Spark is picking up data at 1.5 million points per second. So we're getting lots and lots of data here. Work around any areas that are green. We're a good distance away and we're picking up the right amount of data. When we go red, we're too close. When we go blue, we're too far away. So that should be it. Scan data we're going to see today. Getting a bit of data. We've got the raw data here. First thing we do is do a little bit of trimming. Then here. So do basic alignment. So at the moment, this data is at a random point in space. The scanner doesn't know where origin is. Scanner. Okay. Do simple hold fill. Here, fill. Just we did it quite a quick scan. Spent a little bit more time. We've got a lot more data. So process. Export. Mesh. Save. Okay. All we need to do for our data acquisition here. Next, we're going to bring it into NTOP and open a new file in NTOP and open this custom path workflow. So in this workflow, we take some scan data and set a start point and end point for our cast. Here we've got a point where the cast is going to start. The thumb is going to go cast length, lattice thickness, and we're going to create cast. So this is this cast completely conformably scan data, bring it to NTOP. It's a quick workflow where it's custom. There are a few things that we can adjust. The start point, the end point, the path length. We can also adjust the density. So we've got a point count here to make it more or less dense, the path. You can see here we've got more dense areas here and here at the cast extents. You can see we've got more density here to get further away. Maybe it makes more sense for that to be an injury site. They have more density in the site of an injury. In this case, I can move my injury site to wherever I want, and within the workflow, change the density driver to the injury site. So it's just working with background. In 20 seconds or so, it's going to recreate this custom class with more density around that injury site. So completely bespoke to the individual components. And they can see we've got more density in this area, less density as we get further. So more support in the injury sites, but flexibility and mobility as we get further. We can do the same with the thickness. So at the moment, we've got a uniform thickness of 2.5 millimeters. We can change that with a ramp block as well. So maybe here again, we use that injury site rather than a 2.5 millimeter uniform thickness. Very thick, so we get more thickness injury site. So the magic with this workflow is that we haven't just built a single part here, we've built a process or workflow that's going to take any scan data that we import into NTOP, create a custom cast wrapped around that. So go back to the top of the workflow. Control I to import the scan data. It is scan data, scanner. The Preform applies a smart resolution. So we set the resolution of this STL to 2 millimeters, but the software has done a smart resolution. Any flat areas where we don't need such tight tolerances, we've decimated those triangles to make the file a little bit lighter. Now, in the workflow, at the moment, we're using the initial scan data here to create the final cast. If I just drag and drop our new scan data into the top of the workflow, we're going to rebuild, rerun this workflow again. It's going to take around 20 seconds. It's quite a complex operation. We're wrapping a lattice conformally around the scan data, applying those same constraints that we had before with the injury sites. We're getting a more dense lattice on the injury site. You can see just how quick we rebuilt this cast, wrapped conformally around the new scan data. If we want a cast that's a little bit shorter, we can change all of these parametric units here. So we can change the start point, the start point of the thumb, cast length. So maybe we will take the cast point, it starts a bit further down here. Length, slide it up. Now we're going to rerun the workflow again, rebuild the cast, formally around that scan data. Seconds, what that looks like. The next thing we're going to do is take the model in NTOP, convert it into an STL, where we can hand it over to Moises. Go to our exports, got our body here, that we're going to convert to an STL. We've got a few parameters here for our STL. We set it to a 0.5 mil tolerance. So we could go with a much finer tolerance if we wanted to, but just in the interest of showing you what it looks like in quite a short amount of time, we've converted that into an STL now. You can see we've got some slightly rounded edges. We could sharpen this mesh, spend a little bit more time on it. We're also running a simplification of the mesh as well. So at the moment, we've set a 0.5 mil tolerance to all of these faces. There are some flat faces where we probably don't need such triangle detail. We're going to decimate those triangles. And that's just running the back. At the moment, this STL file is 3 million triangles. The simplification is just running the back. But take it down to folder. Final part, save file. That's where we take the STL file, send it over to Moises, and we'll show you how we get to create the printing of the part.
Yep. Thank you, Joe. Just let me start sharing my screen. Hello, everyone. My name is Moises Arturo, and I'm part of the engineering team here at CREAT3D.
So the next bit of the webinar is going to consist on how we transform this STL file into our 3D printed part. And so the first thing that we need to do is to prepare the file to run it through the slicer, which is Preform. Preform is a free software developed by Formlabs to control of their 3D printers. So this is how Preform looks like. So the next thing that we're going to do is just to select our fuse from the menu. We have a lot of printers, so I'm selecting the fuse. And the powder that we have here created is nylon 12. And the default layer thickness is 110 microns. So after clicking apply, what is going to happen is going to transform the build volume into a fuse 1 plus build volume. Then we are ready to drag and drop our ST file that Joe just exported out of Entropology. I have already prepared a file which contains not only our cast, but other orthotic devices and STLs and smaller parts. So there are some cool features here in Preform. So we can also use a 3D packing algorithm, which is going to do the orientation and packing by itself automatically. We can also use the array function in the case that we want to do some batch printing. And we can also estimate the time that the print is going to take to finish the build. So it's pretty much a big build. And while Preform is doing its thing, then we can also have a look on all of the parts that we are gonna print this time. So SLS Technologies allows us to nest smaller parts inside of our build, so we can optimize the space. As you can see, there are some smaller parts inside of one of the casts. So as long as the parts doesn't overlap between themselves and they fit in the build volume, the printer is gonna print them just fine. So after Preform has finished estimating how much time it's going to take, so here we can see that this particular build, just because it's too big, it's going to take roughly 20 hours to print. And there's some additional time for the build that the build chamber needs to cool down in order for us to eject and excavate the parts out of it. So we can also know how much powder we're going to use and how much powder is going to be transformed into our 3D printer parts. Let's remember that these complex geometries are only possible to be printed in SLS technology because the powder is going to act as the support agent. So now that we're happy after orienting and packing our parts, we're going to upload the job to our printer via Wi-Fi network or USB cable. And then we are good to go to the next step, which is the 3D printing process. Okay, so after uploading the job to our printer, then we can go to the printer and select the queue. I already blacked out some of the files because we run a lot of prints and I just covering the confidential information, but here we can see some general information from the job that we uploaded. We need to do some quick checks every time that we run in the printer. It's just a good practice just to check that we have a build chamber inserted, that we have an IR sensor inserted, that we have enough powder as well. And on the latest update, we need to be sure that the gantry of the printer is clean as well. So we can go back to our job and we can see some general information, how much time it's going to take. This is not the same file that I uploaded, but for the sake of representing how it looks like, then we can see the general information, how much time, the type of powder, how much powder we are going to use for this particular build. So what is happening right now is that the printer is running some quick checks. Is checking the movement of the motors, is homing the build plate, is going to drop the build plate all the way down and bring it up back again. Is checking that the sensors in the build chambers are fine, in the build enclosure as well. Is firing the laser just to check that it's working properly. And then after all of these checks have been done, then the printer is going to start dropping powder from both sides. So this is going to create a thick layer of powder, and then the preheating stage is going to start. The printer is going to be heated up with the help of some quartz lamps that are on the sides of on top of the build chamber. And the printer is going to be taken up to 180 degrees. Right now, we can see that the printer is being preheated. And then what is going to happen inside of the build chamber? So we can go back into our Preform software and we can see the laser in action. So the laser is sintering the latest layer of powder, drawing the sliced file that we just uploaded. Then a thin layer of powder with 110 microns thickness is going to be deposited on top of the previous sinter layer. And then the laser is going to fire again, sintering the new layer of powder. And this process is going to be repeated across the whole build. So now that the print has finished, then we can take the print to our SIFT, which is our powder recovery system. So after waiting for the build chamber or the printer to cool down, we are safe just to transport the build chamber inside of the SIFT to connect it. And we're going to be able to see as well the temperature of the 3D printed parts. So this is how it looks like. It's a solid block of powder, but our 3D printed parts are inside. It's just that the powder has been compressed, and that's why it looks like a block. So I removed a lot of powder from our 3D printed parts, and all of that powder fell below this white disc, which is a tumbler. All of this powder can be recycled. And what I'm doing right now in the video is just scrubbing off as much powder as I can. I'm trying to get as much powder of our 3D printed parts, and I'm pushing it below the white disc. Then we don't need to worry on mixing and weighting the powder that we're gonna mix with the recycled powder, because the SIFT has the ability to do this. So we just need to select the refresh rate that we want to use for the next build, for example, 20, 30, or 50%, according to what Formlabs recommends. And then, well, the SIFT is going to do this automatically. After we have finished scrubbing off the powder, then we are ready to refill the cartridge, which is on the bottom of the SIFT. And then after the cartridge is filled, then we can clean the build chamber just to leave it ready for the next build. So right now, I'm just cleaning the build chamber. If we have another build chamber printing already inside of the fuse, then we can take the first build chamber, insert it into the SIFT, and then put it back again into the fuse and start a second job. So this is where we get our high throughput of parts being printed in the fuse. The last step is just taking the parts that we just printed in the fuse to the bead blast station. And it's just a cabinet with glass beads that are going to be shot on the surface of our 3D printed parts to remove the powder out of the parts. So here at CREAT3D, we like to use a bit of compressed air just to get rid of the dust that still remain on the surface. But after this process is done, then we have our production ready parts which are ready to be painted or sanded or coated with a different material, or to be dyed in a different color. And that's it for me. And well, we're gonna go to the Q&A section, and thanks for your attention.
And we have, do you want to show the brace that we have?
Oh yeah,
printed?
well, after Joe scanned my hand, this is the steel file that Joe did in anthropology, and this is the end product that we 3D printed.
Lovely. Okay, so I think thank you everyone for that. That was really great. I think we've just got a few questions, I believe, that have come in. So just bear with us and we'll work through them.
Cool. So the first question we have here: most of these parts are for Class 1 medical devices. How will these parts or assemblies meet ISO 13485 and the UK medical devices regulation?
Okay. I don't know that Seiko, do you have any insight? If not, we might need to take it away.
I think it's best that we take it away,
perfect, yeah.
considering there's different standards. We do have a lot of medical device customers. However, the responsibility of certifying with the ISO standard, unfortunately, will be with the user. But we can discuss further on what kind of ISO certificates we have right now that we can share with you.
Yeah, thank you for that. We will make a note and we'll contact you with some more detailed information on that for you.
What colors do you provide PA11 and TPU? Okay,
so the question I just hope everyone heard is, what colors do we provide in PA11 and TPU?
Yep. So you might have seen on the screen and potentially the camera. I'm not entirely sure if we're showing the main camera where you can see all these parts. These parts are in gray and they will be provided in gray. And currently most of our materials are in the spectrum of gray to black, simply because the sintering process requires a laser to melt or sinter the powders together, and gray or a darker color is just simply easier to work with.
What is the total build volume of the fuse 30 watt? Is the SIFT necessary or optional?
The total print volume of the fuse one, thankfully, he has kindly taken a note for me because I tend to forget, is approximately 16 centimeters times 16 centimeters times 30 centimeters in height. Is the fuse SIFT optional? when you are 3D printing, with any powder-based 3D printing, you do have to reclaim the powder simply for recyclability, so you can use it for your next print. The process of reclaiming this powder, I think, is best with our fused sift. I would highly recommend it. If it's not too far to say, mandatory. Alternatively, we do have a fused powdering kit. However, I would not recommend it if you are considering production. If you're in production, the bottleneck will be post-processing, removing all the parts, which is the most manual part of the process. I would recommend using a fused sift 100%, and that's the machine right behind me.
And just to add to what Seiko said, one thing with the build formula as well, it's always worth knowing that you can also split parts. So you don't always necessarily have to print everything in one size. So if you've got something particularly large, you can actually print it in sections and then join them together afterwards. And there's loads of different ways of joining, and you can be really clever with your design in joining those as well. And the other thing with the sift is, I would say 100% of our clients have a sift. It really is just much easier. You can also kind of get a lot of throughput through the sifts it's much more an automated process rather than the manual option.
For this specific application, how does FDM compare to SLS 3D printing?
I think that's a wonderful question. I do see some users using FDM simply because it's a less of a, I would say, I don't want to call this a complicated process, but if you're making one part and one part only, yes, I think FDM might be simply easier, considering you don't have to stack the parts and think about recyclability. However, with the users I speak to, considering they're making a lot more parts, the ability to pack as many parts as possible into one build. On top of that, we offer an isotropic mechanical property. So let's take one part as an example, like an AFO. You would imagine if you were to print this on FDM, you're going to have to stack individual layers like this. What happens with FDM is that stacking layer lines that you can visibly see, their propagation points where you can actually tear away and break away easier than the other direction. So there's an aspect of orientation you have to consider in FDM, which you don't have to do in SLS. I think an isotropic or a mechanical property that doesn't differ based on orientation is much suited for applications such as orthotics, where there is an impact and high performance that is required. So that is my personal opinion, but I'm happy to have this discussion in more detail.
I guess you've got the extra design freedom in SLS as well over FDM. So
Absolutely, thank you very much. I got it because I designed so much latticing, and I was like, of course I can print this. I don't even think twice when I'm using topology. But you're right, with FDM, I do have to consider whether it's self-supporting, whereas in SLS, because it's all powder that you've excavated, you don't have to consider all of that. So yes, there is a design added design freedom with SLS over FDM. Thank you.
And I think just one more thing to add as well. I think especially things like the softer, the TPU materials, the quality of the print that you have over SLS is going to be a higher quality than the print that you will have over FDM, simply because of the way in which the technologies work. And ultimately, these are parts that are having to be worn by people, and you always want to try and get the best surface finish, the best quality, the most lightweight out of it as well. So for me, it's kind of that combination why SLS is particularly well suited to this industry.
Is there a minimum recommended strut thickness for lattice structures in PA 11, 12, and TPU?
Yes, I would say it depends on the materials. Also depends slightly on the orientation. Simply for printability, we are using a laser. It's not like you can go infinitely small. And of course, we're using powder grains, which are 55 microns to 110 microns. So I would say, please refer to our design guide. I believe, if I can base it on memory, the minimum wall thickness is around 0.6 millimeters. But I think it's more about what's the it's not about what's the minimum you can print, but what's the application? How much strength do you need? How much shore hardness do you need? And that's where I think we might have to place a bigger importance on, rather than what can the machine do.
One for Joe. How mobile is the scanner?
Yeah, so the scanner itself, we're connected with 2 cables. We're connected to power and to data to the laptop. The power goes into a 3-pin plug, but we have battery packs as well. So essentially, wherever you can take a laptop, you can take the scanner. So you don't have to, I guess in this application, you wouldn't have to have the patient come to a scanning room or a scanning facility, take the scan to the patient.
I've got one here. I've investigated tech like this before, but it was hard to get return on my investment because it seemed really expensive. Any thoughts, any advice on that?
Yes. Yeah, it's a good question. A lot of existing or previous SLS technologies can be cost prohibitive. Really, you're looking, it depends totally on your setup and to what level. But realistically, you're looking from an investment somewhere between 30 and 100,000 pounds, depending on the setup. So for example, the range of the printers, the print setup, so where you've got the fuse and the sift and the system, you're looking at about 40,000 to 45,000. The scanner, you're looking at around 20 to 30,000. So really then it's just kind of how much equipment, what setup is required, and there's lots of variance within that depending on you and your production levels and what you're trying to achieve.
Can we watch the recorded webinar later?
Yes, you can watch the recorded webinar later. That's a tongue twister. Yes, we will be in touch. Actually, we will drop everyone a line who has joined us, and we will send a copy of the recording out as well. Do we have any further questions?
Yeah, there are a couple. Conscious of time.
Oh yeah, just conscious of time.
We've got one more here. What are the advantages of SLS over resin?
Oh, okay.
Every potential technology. I think SLS, well, all 3D printing technologies have their advantages and disadvantages. So I'm not going to say which one's better, but which one's more suited for the application. Resin is a great 3D printer. I'm going to speak specifically about Formlabs SLA, not necessarily about all SLA, but with Formlabs SLA, it's an easiest switch between materials. We offer 30 plus, actually more than that at this point, different materials, and you can switch between resins in a matter of seconds, which in SLS you cannot do. However, with SLA, as you can imagine, you have to print on support track sheets. You have to fit it in one build platform, which is not necessarily large enough. So when you're looking at production and you're looking at certain materials like that you are familiar with, not necessarily thermoset plastics that you may not have heard of, like, oh, it's Tough 2000. Instead, with SLS, you can use material that you're familiar with that's used in the industry, like nylon and TPU, and stack it up efficiently for production. So I think those are the defining factors, specifically in orthotics, if I were to compare SLA and SLS. But that's not to say there are no orthotic companies using SLA. There's actually one of our materials, Durable, who is being used for the production of ankle foot orthosis.
Yeah, and also we've got some customers who will use SLA for early stage prototyping and product development, design development, and then switch to final prototyping and production on the SLS. So again, can be used in conjunction.
Thank you.
No worries. I'm conscious of time, but I think, have we got any more questions?
Couple more.
Just a couple
quick
more?
ones,
Yeah, go for it. Yeah, more quick ones.
Can we provide more information about how to join parts together?
Yes, of course we can. So the question was, can we provide some guidance in joining some parts together? Yes, we can. We will take a note of who's asked that question and take that offline. We have lots of experience on doing that, so we will share our insight and also some guides on it as well.
Cool. And last one, probably for Moises. Can you comment on the comfort of the handbrake?
Oh, well, I want to take it home, but I'm not sure that I'm going to be able to do it because it needs to be in the showroom. So yeah, it's easy to use. I'm happy with it. So yeah, very comfortable to use.
Lovely. Okay, I think that's all our questions. Thank you so much for joining us. As I said, we'll be in touch and we'll also send out a recording of the webinar. Any questions, please do drop us a line. Thank you to my wonderful panelists for joining. I hope you enjoyed it. Thank you very much. Thank you. Bye-bye.
Bye.
Bye.